Okay, Bismillahirrahmanirrahim. In the last class, we started the DFT, discrete Fourier transform, where we have mentioned that if we have our time domain sequence xn, we have done the discrete Fourier transform, and we have found xk. And after having xk, if we do inverse discrete Fourier transform, we'll find xn back. However, this xn is a periodic signal at this moment by the mathematical term. However, for the discrete Fourier transform as well as the time sequences, we target 0 to n minus 1 samples, which means that n number of samples, both for the time domain sequence and for the frequency domain representation. That was the summary from the previous class. And why we should move to the discrete Fourier transform from the Fourier transform, what is the cause behind that? As we have already know that in case of Fourier transform, the result x omega is a function of omega, which is continuous, and practically this is impossible to store all the data in the computer when omega is an analog. On the other hand, in case of discrete Fourier transform, we are discretized this omega in such a way that omega can be replaced as twice pi by number of samples multiplied with k, where k represents 0 to n minus 1, which means capital N number of samples. If you have any question or comment based on the previous lecture. Okay, it seems everything is fine. So we have shown in the last part of our last lecture that this is our input xn. At the end, whenever we have done the Fourier and then we do the inverse discrete Fourier transform, now the xn looks like this. So it will be a repeated function where we need to concentrate to 0 to n minus 1. So this is the 0th sample and this is n minus 1 sample. We do not need to care about after n minus 1 or before 0th sample. So this remains stand still here at the same time domain as well. Okay. So now in this topic, we'll discuss about the process to derive the inverse discrete Fourier transform. We have already shown mathematically how to represent the inverse discrete Fourier transform. However, here we can prove it with some notation. Okay, so let's take this is xk multiplied with wn. This capital N represents the number of samples to the power minus kn, where k is from 0 to n minus 1. And now this xk, what is xk? We already know that this xk is nothing but your xn multiplied with w to the power kn, and we have this notation capital N to represent how many samples we are targeting, and the summation where k is from 0, not k, n is from 0 to, so that is of course n is from 0 to capital N minus 1. This is by the definition of the DFT. So we actually replace this xk, capital Xk, with the same principle, with the same values, where this n is equals to L, because n is a dummy constant, so you can replace it with any constant, any alphabet. So we are taking n is equals to L. And now if you look at closely what we have done here, this function is a function of L, but is not a function of K. So that's why we can take this part, that means this summation, out of the box of this one, because this part is not a function of K, but this part is a function of K. That's why we can write in this way. So this will come here, and the summation can be implanted with the Wn to the power KL, and W to the power KL multiplied with W to the power minus KN. So we can write in this way. Yes, for this one, let me take it out. For this one, we have this W to the power K L minus N, where if we do the mathematical calculation, as we already know that what is a Wn, this is an exponential term. For that one, just do the trigonometrical part, elaborate the function. For that one, what we have found, for L is equals to N, for only for that case, we have the value. That means for L is equals to N, in that case, we have e to the power 0. That means this is equals to 0. E to the power 0 means 1. And how many ones we have? We have n number of ones. So if you add 1 plus 1 plus how many? So of those, n number of that, so it will give the summation is equals to capital N. So we got the summation is equals to capital N. Okay. On the other case, if L is not equals to N, in that case, we got the value is equals to 0. And that's why summation of all the zeros definitely gives the output is equals to 0. And that's why it is the 0. So there are two cases. Only for L is equals to N, we got this is capital N, and otherwise that is 0. So what we can found here, what is this? This term is nothing but xn, that is the full time domain sequence, and multiplied with capital N. And this capital N actually came from here. From this expression in the left side, what was we have previously? We have this term. We start with that term. So we can write this term in the left side. That means this is xk and wn to the power minus kn, where k is equals to from 0 to n minus 1. So if this is the equation number 1, what we can write, what is the value of xn? So easily we can write xn is equals to this from the previous equation, and which is nothing but the inverse discrete Fourier transform. So that means if we have xk in our hand, we can find our time domain sequence, and we'll show a very practical example in today's lecture, inshallah. Okay. So this is the proof of the inverse Fourier transform. I'd like to request you to understand this part, because it will come again and again. Why I'm writing that if L is equals to N, that is equals to definitely Wn to the power 0, and Wn, that is what is the value of this? This is e to the power minus twice pi divided by n. So that is the value. So and this is into 0. So of course e to the power 0 is equals to 1. So how many ones are there? So n numbers, so that is n. On the other hand, if L is not equals to n, so why that is equals to 0? Just express it yourself and you will find the answer. Okay, so now and then we'll use this concept in case of discrete Fourier transform. Now it's better to start with some explain the things with few examples. First example always is a very important example, that the delta function. Okay, so for the delta function, what we have at n equals to 0, at n is equals to 0, we have the sample. We have the sample. Otherwise, we have the 0. And now, since in case of discrete Fourier transform, it actually works for this xn, it should work for how many samples? Capital N number of samples. So we need to pair it with some zeros, and you can define how many samples you are considering. Let's say you are considering 1, 2, 3, 4, 5 samples. So you need to declare it. So how many samples you are considering? Of course, for the delta function, the result will be the same in any cases, whether you are taking a single sample or a double sample or an infinite number of samples, the result will be the same. So in future, you will understand why we need the zeros. This is called padding zeros. Eventually, you are putting some zeros. That means you are defining how many samples you are taking. Okay, so that means you are defining what is the value of the capital N. For this case, that is 1, 2, 3, 4, 5. Okay. Okay. So we are paired zeros from 1 to n minus 1. So that is important. Okay. After that, by definition, we can declare what is a discrete Fourier transform. Delta n multiplied with w to the power kn by definition, where k is n is from 0 to n minus 1. This is very simple because this is true only for n is equals to 0. So we got the value is equals to 1 for all the value of k. So that means what you can write here, let's say the capital N is equals to 5. In that case, what is the value of capital K? Capital K. So the K is also from 0 to n minus 1. That means 0 to 4. So how many values you are getting in xk? So you are getting how many samples? You are getting 1, 2, 3, 4, and 5 samples, where all the samples having the result 1, because it is not a function of k. So that's why the result is 1, 1, 1, 1, and 1. If you took this capital N is equals to 50, then the k is from 0 to 49. So how many ones you are getting? You are getting 50 ones are there. So you get 50 ones. Let's say this is the 0th one, this is the first one, and this is the 49th one. So no matter how many zeros you are taking for delta function, so it will not impact to the result. However, for many cases, this number of padding 0 will make some impact to the result. Okay, so make it simple that for this case we are taking a number of 0 padding, no need to care about that, and we got the result like this. And now the question is, are you happy with this? This is the response in the frequency domain. How you can justify that, yes, I am happy with the previous experience. If you can recall, if you have xn is equals to your delta function, how it looks like, the magnitude response of the h omega, x omega. Of course, you can understand that it was 1 from minus pi to plus pi. That means if it will repeat again, what will happen if I consider from 0 to pi and twice pi, what will happen? It should be a continuous 1, because the delta function, to build the delta function, you need all the frequency component with a same magnitude, and the magnitude is 1. So now, according to the discrete Fourier transform, now this will be discretized. And how many samples? You have actually defined those samples. And this is the discrete Fourier transform. And it looks like, yes, we are happy with that, because the magnitude should be 1 everywhere. And this is the result, and the plotting is there according to the result. Now, what about the magnitude response? Yes, you can find the magnitude. And what about the phase? Phase is definitely 0, because you don't have any imaginary part. So now we can say that, yes, I am happy with this answer. Now, if we shift the delta function, what will happen? We already know that whenever you are shifting your signal, that will not change the frequency. It actually changed the phase. So what we can expect, the magnitude response should be remain the same, but the phase will change. Okay, so what we can do, we can go for straightforward mathematical expression for the discrete Fourier transform, and which is like this. And of course, this only carry the value 1 at the location of n equals to m. And for that, we got this result. So xk is equals to this. Now, what are how many samples you have in the k? Definitely, we already mentioned that in general, that is from 0 to n minus 1. Now, putting this value k. So if k is equals to 0, it gives the value 1. If k is equals to 1, this is wn to the power m. What is wn to the power n? This is e to the power minus twice pi divided by n into m. And where m is a constant. If that is shifted, let's say this is the 0th sample, this is the first sample, and this is the second sample, that means it is shifted for 2 samples. So here m is equals to 2. You need to understand each and every part whenever you are writing it in the mathematical expression. So this m is equals to 2. So now you can write it in this way, e to the power minus twice pi divided by n into 2. Okay. Again, what is n? As an engineer, you have already defined that. If n is equals to 5, then again, we can write e to the power minus twice pi divided by 5 into 2. So of course, this is a value. And you can find where is the phase. This is the phase. You have find the value. Of course, there is a j part is there. So e to the power j is there. Okay, so phase. So you'll find the phase minus twice pi divided by 5 into 2. So this is the phase value. You got the phase value. Okay, for this one, the k is equals to 2. So you can go forward and up to k is equals to n minus 1. If n is equals to 5, that is 4 into m. You got the value. And this is the result. Now the question is, are you happy with this result? Yes, you can compare this xk with x omega. You already have this experience before. Try to go there and try to match with that result. Okay, and you have found that, okay, this is exactly the same what we have found in case of Fourier transform. In the previous example, okay, so we start with the delta function. In the time domain, how it looks like, the delta function, we know that this is only a single sample. Now comes to introducing another example where xn is equals to a cos function, cos twice pi r n divided by capital N. Okay, so try to understand that how it looks like in the time domain. Of course, it is a continuous signal. It is a continuous signal. It actually goes to infinity and comes from the negative infinity. and that is a cause signal. And this part, if you closely look at this, we have cause. It looks like twice pi by capital N into R into N. So this N basically define the samples. This is a digital samples. Okay, so this part defines the samples like that. Okay, and this whole part is defining, we have cos omega N. So this omega is defining as twice pi by N into R. Okay, you need to understand this. So this frequency, relative frequency, is now defined as a twice pi divided by N into R. Of course, the frequency depends on the value of R. The frequency of this signal depends on the value of R. If you increase the value of R, of course, it will increase the frequency. If you decrease the value of R, it will decrease the frequency. So ultimately, we should find that our ultimate result, which is xk, that should be a function of R. That what we can expect, because twice pi by N for a particular case, this is constant. This part is constant. Why? Twice pi, of course, this is constant, and divided by N. Before starting this example, you need to define what is N. So you are actually defining or fixing twice pi by N. So this is constant. The part N, this is actually not depending or defining the frequency. That is only to defining the samples. What is the factor which actually differ this equation from one frequency to another frequency? That is only the R. Okay, so that should be a function of xk. Let me start the example. By using the Euler's formula, always it helpful to do it in the exponential term, taking the exponential term for the Fourier transform as well as for the discrete Fourier transform. So from the Euler's formula, we can write it very easily here, and afterwards, this is our xn. So we do some pre-processing. Okay, so what is a Wn? We already know what is Wn. Wn is e to the power minus j twice pi divided by capital N. That is the value. So we can convert it with respect to Wn here. After that, what is our task? This is our xn. Now we are doing discrete Fourier transform. So according to the formula, what we are doing here, this is the xn part multiplied with Wn to the power kn. Here is the xn part, the second part, and Wn to the power kn. Since this is a linear LTI system, of course, we can add those terms together. So we can add those terms together. Of course, this is half is a constant. Again, this is a linear LTI system. So now we can do the multiplication and addition accordingly. Okay, so just follow the mathematical path. What we have found here, the first term looks like this and the second term looks like this. Now concentrate again, as we have already shown earlier, that if k is equals to r, at that moment, this is equals to, this actually gives 1. And how many ones are there? N number of 1. So that's why the summation will give 1. At k is equals to r. This is very important. On the other hand, if you have this this k is equals to minus r, k is equals to minus r, at that moment this belongs to 1, and which gives n. Similarly, k is equals to minus r means that the k is equals to minus r plus n, because as you know that the sample k will repeat after n samples, because that is a periodic function. What does it mean? In case of Fourier discrete Fourier transform, it starts from 0 to n minus 1. Let's say it looks like this. It looks like this, and it will repeat again. I should write it in this way. Okay, so it will repeat again after n minus 1. So it will give the same thing again. Okay, so after n samples, it will repeat. So what does it mean? At this point and this point, they are the same. So this point and this point, they are the same. So after how many samples this repetitions actually been done? After n samples. So if we say that at k is equals to minus r, this is happening, it is also true that for k is equals to minus r plus n, it will happen the same thing again. Okay, so that's why we can write that the k is equals to minus r, that is equals to k is equals to minus r plus n, which is equals to n minus r. What does it mean? In the graphical notations, we will show that. Okay, so first of all, let me clear it up that at k is equals to r, the amplitude is n. For k is equals to n minus r, the amplitude is again n. And for both of the cases, that is multiplied with half. So how we can represent this in the wave shape or in the magnitude platform? So this is the summary. For k is equals to r, this is n by 2, the amplitude. For k is equals to n minus 1, the amplitude is equals to n by 2 again, and otherwise this is 0. And it can be shown in the graphical representation very, very easily. Try to understand that. Where is at k is equals to r? This is this is a k x-axis. At r, where this is k is equals to r, the amplitude is n by 2. This is true. Okay, so we have counted this. And the second one, at k is equals to, previously it was mentioned k is equals to minus r. Where is that? This is k is equals to minus r. At k is equals to minus r, the amplitude is equals to n by 2. However, this is not in our range of view. What is our range of view? Our range of view is from 0 to n minus 1. So we need to find where is the repetition. So minus 1 is again repeating at n minus r. Minus r is repeating again after n samples at n minus r, and the amplitude is of course the same, n by 2. So if we have something in the out of range, we need to search where is the actual range where we can find the repetition again. Okay, so here we have found, and finally what we have found, that we have two stems at the location of r and at the location of n minus r. Now the question is, let's say r is equals to 3 and we are taking n is equals to, let's say, 10. So 10 samples and r is equals to 3. So we can define that this r, so this is 3, and n minus 3, which is equals to 10 minus 3, which is equals to 7. And this sample is at the 7. So if I want to draw it here, so try to understand this very, very precisely, what we have done here. This is the 0th sample, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So this is the scale of k. what is our range of view? Let's say capital N is equals to 10. So first of all, this is from 0 to 9. So this is n minus 1. And where we have found the stem, let's say r is equals to 3. So we have found the stem at r equals to 3. At r equals to 3 there. And amplitude is equals to n divided by 2, which is equals to what is that is 5. And the second one is at the location of capital N minus r, which is equals to 7. So at the location of 7, we have n divided by 2, which is equals to 5. Now the question is, are you happy with this result? We start with xn is equals to cos twice pi r n divided by capital N. I have mentioned it that this can be written as cos twice pi divided by n, that is a constant part. R is a variable and n is for the making the representation of the sample. I have also mentioned that whenever we have found xk, that should be a function of r, and we have found that. Yes, if you are changing the value of r, let's say r is equals to 4. What happens? Now, if r is equals to 4, it will be there. Try to understand this. And 10 minus 4, this will be 10 minus 4, that is 6. Where is that? It will be there. Okay, it will be shifted. So where we are, what is our range of view? Our range of view is from 0 to 9, where this is the middle one, isn't it? This is the middle one. Okay, probably 0 to 9, we should say. How we got the middle part of that. So 1, 2, 3, 4. 1, 2, 3, 4. So that could be the middle part of that. And you'll see that for the black one, for the first one, you'll get the symmetry. You'll get the symmetry. So this is the boundary. You'll get the symmetry with respect to this. What is the distance here and the distance? So basically, they are representing the same frequency. Previously, what happens if we go for this minus r? Where is minus r? This is -1, -2, -3. Where is the minus r? For the previous case, that was, okay, let me erase this part. This is n divided by 2, which is equals to 5, and this is minus r. Minus r is equals to -3. And this one is repeated. This is the thing, it actually been represented here. So previously, what we have done in case of Fourier transform x omega, what we are expecting whenever we have the cos some signal, let's say omega n, or sine omega n, how many stem you are expecting? How many stem you are expecting? You are expecting a single stem, isn't it? Because that is the single frequency component. The xn is a single frequency component, and we have found it here. For the mathematical concept, for the Euler's identity, we also have the same thing at the negative frequency. We got it in the negative frequency. Okay, fine. This is for the cos. And now this negative part is now transferred to the positive one based on the definition of discrete Fourier transform. Because in case of discrete Fourier transform, the range of view is always from 0 to n minus 1. That's why we need to shift it to the right. And now if we go back to the do the inverse discrete Fourier transform, you need both this component and this component to get back your original signal, because from xn you have derived this one and this one. If you want to go back to xn, obviously you need this one and this one, both of those. Okay, so I believe you understand the process, of course. And if I give this kind of example, let's say xn is equals to sine twice pi divided by capital N p into n. Of course, you can do the process similarly, plus let's say cos twice pi q into n divided by capital N. How many stem you can expect? How many stem? Definitely you can expect one stem for sine, another stem for the cos. Again, for the Euler's identity, you are getting another stem for the sine and another stem for the cos with respect to p and q respectively. And that what we are expecting. So you can do it yourself. So take it as your homework. So xn is equals to sine twice pi p n over capital N and cos twice pi q n over capital N. Try to find the xk, and for different value, let's say p is equals to 2 and q is equals to 4 and capital N is equals to 20. For this, you can draw the magnitude response. Please draw the magnitude response of xk. Okay, then the whole idea will be very clear to you. Any question at this moment or any confusion based on the current lecture? Okay, it seems okay. Okay, so I have already discussed this fact that you can relate this notation with your previous experience. That means it can be mentioned as this. It can be also mentioned as this, where small f is equals to f by fs, or you can also represent like this, where twice pi by capital N is constant. So R is the deciding factor for the signal frequency. Okay, so here it capital N might looks like the fs. Okay, where fs always is a constant value. For our case, that is also a constant value. Now we can discuss a very simple example, but try to understand each and every point of it, so that for the complex processing, you can also done it properly. Okay, let's start with this known expression. So xn is equals to sine twice pi f over fs into n. I believe that everyone know these things very clearly, and you can draw this a signal. Let's that the f is equals to 1 hertz. What is capital F? Any of you? What is capital F? Can you hear me?
Sir, original signal frequency.
Sorry?
Original signal frequency.
Original signal frequency. So that is the analog frequency we are processing. Thank you. And Fs, what is Fs? That is the sampling frequency. We let that. This is the analog frequency and this is the sampling frequency. Nice. For one cycle, number of sample is definitely 4, because it actually defines from the sampling frequency. So we can draw it. So this is our signal. This is our signal, a single cycle. where we have defined that this is the samples. These are the samples. Okay, you can also define here. However, the full cycle actually represent from 1, 2, 3, and 4. This is the fourth sample. Okay, these are very known to us. Now, what we try to do, we are planning to find the samples, and afterwards we are doing the Fourier transform. Okay, xn is equals to, whenever you are sample it, of course, it is x0, x1, x2, and x3. It represents what is the value of it. So try to understand it. These samples and sine twice pi f over fs into n, they are the same. Here it actually represents with a function, and here it's represents with the value. Where by this expression, we already know that the maximum value is equals to 1, because whenever we are writing sine twice pi f over fs into n, what is the magnitude? The magnitude is equals to 1. So the highest magnitude is 1. So we know all the magnitude of each and every point. So x0 is 0, x1 is 1, x2 is 0, and x3 is equals to -1. We have plotted it and we got the actual value. Okay. Now, what is the next step? We have defined our xn properly from the expression. The expression was again sine twice pi f over fs into n, where f is equals to 1 hertz and fs is equals to 4 hertz, which means that in a full cycle we have 4 samples. Okay, we have already defined it, and from there we have found these samples. Here I should write it in this way: n is equals to 0, so we should mention this arrow here. Please mention it, mention the arrow. Okay, next step, what is xk? So according to the formula, we can write it in general, where capital N, now capital N is equals to 4, we know that. So this is from 0 to 3, and xn and wn, since we know that n is equals to 4, we can even write w4. Okay, and this is good culture or good practice, that w to and the subscript should be 4. This is k and n. So in the next line, what we have found there, we need to find what is our target. We need to find what is the range of k, 0 to what? 0 to 3. So we need to find x0, x1, x2, and x3. And then we can plot it. So the things are very simple. So we found x0, and ultimately we found that the x0 is equals to 0. Good. Similarly, just put the value, and you can find that x1 is equals to -2j. -2j. Okay. So as it is expected that in case of sine signal, in case of sine signal, if we talk about x omega, what we are naturally found in case of Fourier transform, we are getting a positive value and the negative value. That is expected. So similarly to that, we are getting what? We are getting 0 at x0. So this is k, sorry, xk. This is x0. What about x1? This is a -2j. Okay, so j shows a phase. If we talk about the magnitude, it gives the value 2. So this is the location of x1, and the magnitude is 2. Magnitude is 2. For x2, that means for this location, this is x2, we got the magnitude is equals to 0. And for x3, we got 2j, which represent that the magnitude is equals to 2, again positive. So 2 positive. So this is for the location x3. Try to understand that always there is a repetition here. Always there is a half of this section. Basically half of the section, we need half of this section. Where is the repetition? So we can understand that. So we need only this section. We need this section. So otherwise the other sections actually gives the repetition. Okay. Let me draw it here. So it has been drawn here, and you can find this is for x0, x1, x2, and x3. Okay. I have also written the frequencies. Don't care about this at this moment. Okay. Don't care about that. So are you happy with this expression or the outcome? The answer is yes. We should be happy with this expression, because what we are expecting, our xn is a sinusoidal sine twice pi f over fs into n, where f is 1 hertz. F was 1 hertz. So we should get a single spike. And this second spike is the repetition, nothing else. Because in conventional way, whenever we have this spike, we should have another spike there. And since the capital N is equals to 4, so after 4 samples, it will repeat again. So that is this is 1, 2, 3, and 4. So it actually repeats after 4 samples. So then what we have done, we are canceling this because that is not our range of view. So this is our range of view, and we got everything over this. So it shows that we have a spike. We should got a spike, and we have that spike here. Now the task is, so this is the process. We start with xn and we come up with xk. Now what is our task? We need to go from xk to xn. So that is called inverse discrete Fourier transform. So we can do it again. So this is the expression for the inverse discrete Fourier transform. Since we know the value of capital N, we place it there. We know the value of capital N, so we can express it like this. And we already know the value of capital X0, X1, X2, and X3. Put those values and you have find what? 1. What is that? This is Xn magnitude. Yes, we already know that previously. We start with sine twice pi f over fs into n. What is the magnitude? The magnitude was 1. So we are happy with this result. You can check that, yes, the result is correct. Number 1. Number 2 is, what is the frequency? How could you find the frequency? Okay, this is very important. I believe you understand how to find the magnitude. The simple formula, that means inverse Fourier transform formula, and you know all the values like capital N, you know xk's are there, that means x0, x1 up to x3. So that means you know actually everything. So from there you can find the value of xn, the amplitude of the xn. Okay, good. Now the question is, what is the frequency of xn? From this value, let's say you have this. I have marked this frequency. Forget about this. If you do not know about the frequency, how could you mention or how could you find that what is the frequency of xn? What is the frequency? Okay. As we already know that the jump of the frequency can be defined as twice pi divided by capital N, isn't it? This is true for all discrete Fourier transform. So the jump, or that means the distance between these two from the frequency perspective, that is always twice pi divided by capital N. What is the frequency at the center, at the beginning? Definitely that is 0. So then what is the frequency at this point? That is twice pi divided by N into 1, isn't it? So the frequency is twice pi divided by capital N into 1. What is the frequency at this point? We can write in this way, twice pi by N into 0. Okay, of course, that is equals to 0. Now comes to this point. What is this frequency? What represent this twice pi? What is the actual frequency of twice pi? What is the actual frequency at pi? What is the actual frequency at pi? Whenever we are representing the things at minus pi to plus pi, what is the actual frequency at pi? With a relation of Fs, because Fs is always known. Any of you? What is the actual frequency at the location of pi? Very unfortunate.
Fs
Yes.
divided by 2.
Fs divided by 2. Thank you. So at this moment, this is Fs divided by 2. That is the actual frequency. So at the location of twice pi, then what is the frequency, actual frequency?
Fs.
Fs. So if that is so, then this twice pi can be represented as Fs divided by capital N. What is the value of Fs? For this case, for this example, what is the value of Fs? 4 hertz, isn't it? 4 hertz. And what is the value of capital N? That is 4. So then we can say that that is 4 by 4, that is 1 hertz. So this point represent 1 hertz. Similarly, if we want to show what does this point means, if your stem, for example, if your stem is your stem is standing here, if it is so, let's say this is the point, it is standing here. In that case, what is the frequency? We have found twice pi divided by N, that is the jump. And how many times? 2 times. So then we can say that Fs divided by capital N into 2, which is 4 hertz divided by 4 into 2, which is gives 2 hertz. So that's why I'm writing 0 hertz, 1 hertz, 2 hertz, and 3 hertz. So more than 2 hertz is not possible. We can understand that more than 2 hertz is not possible. So this is the symmetry line. So they will have the same distance from that symmetry. So this is a very simple example, but I believe that this explains many things. Okay. Now your task, whenever you will return your script, please do it. Do the same thing for Fs is equals to 8 hertz and N is equals to 8. On the other hand, for Fs is equals to 4 and N is equals to 8. Okay, so please do it carefully with the graphical representation. That will help you to understand the process. Okay, so take your time and do these 2 examples